Welcome back to today's video. In today's video, we're going to discuss how we can handle text and categorical attributes in our pandas data frame object. In particular, we're going to take a look at the ocean proximity column that contains non-numerical data. As you can see, it contains data that is non-numerical in nature, and we're going to discuss how we can convert this data into numerical values that we can use to feed into our machine learning model. Before we end today's video, make sure you hit the subscribe button down below and like the video for more content just like this. Let's get right into it. All right, so let's take a look at the content that we're discussing for today. And remember, in the last lesson, we discussed data cleaning. In particular, we were discussing how we could fill in missing values or null values in our data values, and how to substitute values for those null values. In particular, we used the median as the value that we would substitute in for any null value. Now remember, the median would simply calculate the median value for an entire column of data. And so remember, if let's say this particular data value was null, what we did was that we didn't identify that it was null, and then we were able to calculate the median for that entire total rooms column in our CSV file or data frame object, and then we were able to substitute that median value into that position rather than simply leaving it blank. Now, when we did that, we used the simple imputer class in the scikit-learn library, and we were able to calculate the median values for every single column, and we were able to push that into that particular attribute, statistics underscore. And then once we were able to do that, we were able to push it back into the into the pandas data frame object, and we're able to print it out, and we're able to see that below. Now, when we did that data in the last lesson, we excluded the ocean proximity column from our object. We excluded that, and the reason for that was because we cannot calculate the median of a non-numerical column, of a column that contains non-numerical values. And so because of that, we had to exclude that particular column from our calculations. But in today's video, we're going to discuss how exactly we can include the ocean proximity column in our data. Up to this point, we've so far been ignoring it, but we're going to talk about how exactly we can convert this categorical data or alphabetical data into numerical data. Let's just take a look at the data to begin with, and you can see here on the far right side that you notice a characteristic that you're seeing in this ocean proximity column, and that is that many of the values are repeated. You can see here that for the first here, almost for the first 30, let's see, how far does it go down? It goes down quite far, right? So it goes down for quite some time. For the first many attribute, it says near the bay. And then when you scroll down even further, it says inland. And then it says near the bay, and then back to inland again. What you're noticing here is that you're seeing that many of these data values are repeated data values. You see some of them here are less than 1 hour away from the ocean. So you're seeing that many of these are repeated values. And so because of that, there is a possibility that we could simply replace each of these values with numerical values. And so in this case, I believe we have about 5 different variations. We have near the bay, we have less than an hour away from the ocean, we have inland, meaning that's inside of the California area. We have about 5 or so different ones. If we could find a way to replace those categorical attributes with numbers that are associated to them, that might be very helpful. And so let's take a look here at what we have here. So let's go ahead and first start off. We can print it obviously, but we already analyzed the data. So let's take a look here at the OriginalEncoder class. And one of the reasons why we're using these libraries, such as the scikit-learn library, is because it provides much of this functionality as well as many of these classes for us already. And so that way we can focus mainly on the data manipulation rather than coding the implementation for these individual functions. And so what does the OriginalEncoder class do? Well, the OriginalEncoder class allows us to do just what I described. Label each of the categorical attributes with numbers. And so you can go ahead and import the OriginalEncoder class in your Jupyter notebook. And then from there, you can create a new OriginalEncoder object. And each time you do something like this, it creates a new object. Remember that there, it creates a new object. And then we can run a function against this OriginalEncoder. we're going to be running the fit underscore transform function. What this fit underscore transform function does is that it learns the individual categories in this particular column. And once it's learned those categories, it replaces each of those categories with a number. So that's what it's able to do. And then it returns here it returns here the object, and we're going to print that out there, housing underscore cat underscore encoded. So it's going to return back the entire data frame object. Let's go ahead and print that out. Let's go ahead and print out actually the first 10 rows, 10 rows. That way we can easily just see the first 10 rows. So you're seeing here that, sorry, it returns a list. Sorry about that. I forgot about that for a second. But it returns a list. It's a multi-dimensional list here. You can see here that it's a 2-dimensional list. And what you're seeing here is that you're seeing for the first 10 rows, what number is it given a label with? And remember, the reason why you might be looking at this, you might say, okay, this is 1, and then 4, and then 1, but that doesn't make sense since these data is near the bay, near the bay, near the bay. So why might that be the case? Why shouldn't it all be 1 going for a very long time? Well, the reason for that is, remember, we were able to stratify our housing data frame object in a previous tutorial. And when we were stratifying that data, remember that the order that the data was listed in changed. And so if I try to print out the entire housing data frame, let me go ahead and print out the first 10 rows, right? Let me go ahead and print that out, the first 10 rows. Remember that the first row in this data frame object is the 12,655th row. So 12,655th row. And so that 12,655th row corresponds to a categorical, a numerical number of 1. And so why don't we go ahead and go to that particular row, 12,655. So remember, our data frame, this CSV file contains about 20,000 rows. So we're going down here to 12,600. Let me scroll down a little bit, 12,600. All right. 12,645. Okay. So if we go down to that column, right over here, all right, right over here, we're noticing that it says inland, inland. So we see there that the number 1 corresponds to inland. So we were able to get that. And then if we look down at the bottom here again, you see here that the number 1 here corresponds to the 3rd row in the data frame. And that would mean that that would correspond to row 2,908. So row 2,908 should be inland as well, since the same categorical attributes, in this case 1 and 1, right over here we have 1, right over here we have 1, those should correspond to the same numerical attributes. And so there we have 2,908. Let's go ahead and take a look at that. 2,908, let's go ahead and scroll up here, just so that I can show it to you guys. 2,908, all right. Okay, 2,908. Okay, so this is the row right over here. And when we see that, that's also inland. And so you're seeing there how these numbers right over here correspond to these rows that we have in this housing, okay, in the housing. And that's what we're able to pass in. We pass in housing underscore cat, and housing underscore cat, if you remember that one, is actually includes the, remember we did the stratification. When we did the stratification, we were able to include which particular strata each of the columns belong to. And so we would just get an additional column, although I think we already reassigned it. Although we didn't yeah, we already did reassign it. So it doesn't really matter. Housing underscore cat are the same thing in that case, okay? We did that in a previous lesson. Okay, let's go ahead and print that out again. And so you see there, these are the columns. Each of these numbers are corresponding to the individual rows, okay? So that's how it would be like. So we were able to get that data, and we were able to successfully get that data there. Now, from there, what we can do is you might be wondering, how do we had to look through every single row in order to find this. Where exactly is this sort of mapping stored in? Where exactly is this stored in? Well, when we actually run this function called fit underscore transform, what exactly it does is it actually stores the values, each of these values, 1, 4, 1, 4, each of these values, each of the unique values in an array. So once we're able to do that, we're able to see what, how many unique ocean proximity values there are. So in this case, you're looking through this, and it looks like there's around 3 or 4 unique ocean proximity data values. But if we're able to print this property from the ordinal coordinator that we set it right over here, or ordinal encoder, or ordinal encoder, if we're able to print this property, we're able to get the number of unique data values in that column. So let's go ahead and print that out there. You notice here all the unique properties. We have less than 1 hour away from the ocean. We have inland, island, near bay, and near ocean. So we have 5 variations. And so in this case, using the ordinal encoder class is very helpful, because using the ordinal encoder class, we are able to, in this particular case, is we're able to assign each of these categories and kind of simplify them down like this. So it is very helpful now that we're able to know the different properties. And this categories attribute, by the way, when is it set? Well, it's set when we call this function fit_transform. That's when this function is set. Okay, so we're able to get that. So it's a 1D array of unique data values from the ocean proximity data values. Okay, all right. So this is much better than what we had before, yet there is still a problem. Is that, let's say we try to push this data and try to add a column to our data frame. So we can add a column very easily. We could say something like housing ocean underscore proximity. We can just replace the existing column ocean underscore proximity, and we can say it's equal to housing underscore cat, or housing underscore cat. We can just pass that in, right? So but in that case, what's the problem? Well, the problem is that the data might start observing correlations. The machine learning model might observe correlations where those correlations simply do not exist. And the reason for that is, let's say we have the numbers 3 and 4, for instance, the numbers 3 and 4. So 3 corresponds to what? Well, 3 corresponds to island, right? It corresponds, or sorry, not island, but near the bay, since the indexing starts from 0, near the bay. So it corresponds to near the bay, and then 4 corresponds to near the ocean. Okay. Now that wasn't a very good example, actually. Let's do this one. Less than 1 hour away from the ocean and inland. Less than 1 hour away from the ocean is 0, right? 0 is the index. Inland is what? Inland would be 1. Well, in that case, does that mean that inland and less than 1 hour away from the ocean are close to each other? Well, no, they're not close to each other. They're actually very different from each other, right? But since they're given a value of 0 and 1, the model might assume that they're very close to each other, right? But in reality, they're not very close to each other in any way whatsoever. And so because of that, using this type of numbering may not be optimal. And we've done this many times so far, is that we'll arrive at a conclusion, but that conclusion is not entirely optimal for our particular use case when we consider other factors. And so one of the factors that we have to consider is, will the machine learning model derive certain conclusions from using 1 and 0 to represent less than 1 hour away from the ocean and inland, when those conclusions simply should not be derived upon. Okay, so we don't want to derive those conclusions. And so the way that we can solve this problem is actually by using something called OneHotEncoding. OneHotEncoding is basically a way where we can assign a particular data value with being the number 1, and all other unique values will be set as being 0. Okay, so one unique data value is going to be set as being 1. All other data values are going to be set as being 0. Now, the data value that we set as being 1, this is called one-hot encoding, the data value that we set as being 1 must be the most unique value out of all the other values. So all the other values, preferably, ideally, or preferably at least, should contain some similarity within them. Hence, they're labeled 0. And so the 1 is called hot and the 0 is called cold. When we're looking at this data, which one of these particular values do you think we should label as being 1? You're looking at this and you see near the ocean, near the bay, island, and inland, and less than 1 hour away from the ocean. Well, the one that I'm noticing as being the most unique is inland. You can see here that less than 1 hour away from the ocean, that's near the water. Island is obviously near the water. Near the bay is also near water. Near ocean is also near water. Now remember, the goal here, keeping the goal in mind here, what's our end goal, is to predict the median house value. And just from your own understanding, without even analyzing our particular data, houses that are more closer to oceans may be more expensive, right? And you're seeing that four of these particular elements, rather, in our list here are near the ocean or near the bay in some way or another. The one that's the most unique is the inland. Inland is the most unique. And so the best idea would be to assign inland as being one. Why is this going to be helpful to us? Well, when the machine learning model is going through our data, it might be able to notice that, hey, as house prices go down, that also corresponds to it being the house being inland, right? Whereas extremely high house prices might be near the ocean or near the bay. And that's assigned with 0. And so it's able to derive meaning from these numbers. And deriving meaning from numbers is the most important thing that you want to do for your machine learning model. Because remember, the machine learning model that we're working with is going to be fed numerical data. And we want to work with numerical data. And we do not want to work with text data. So we want to convert this into numerical data that is meaningful in nature, such that the machine learning model is able to observe correlations that exist and is able to discard correlations that may result in certain similarities between things occurring when there is simply no similarity between them. And so using the 1, 4, 1, 4, using the 0 through 4 is a very suboptimal solution that would provide very, very little to no meaning to our machine learning model. Whereas using 1 and 0, that would provide a great deal of meaning to our machine learning model. So let's take a look at this here. We have the OneHotEncoder. And again, the goal here in the machine learning here is not necessarily to implement these solutions in terms of implementing the solution. Like, okay, for example, you could say, okay, now that we've gotten these values 1, 4, 1, 4, 0, now we need to implement one-hot encoding. And if you're even like a decent programmer, you should be able to implement this solution without using the scikit-learn library, right? You should be able to implement the solution. You can just say, okay, which values are, you can just loop through every single element here and just say whichever values are inland, call it 1, all the other values are 0. You don't have to be that great of a programmer to do that, right? But the thing is that our goal is not to implement these solutions. Our goal is to think about ideas and have the library, in this case, scikit-learn, implement these solutions for us, rather than us implementing these solutions. We're simply focused on the capabilities of the class or the library in this case, the capabilities, rather than the actual mechanics behind why it does stuff. Now, you might need to know, for instance, that when you call the fit underscore transform function, it updates a particular attribute called categories, which allows you to print the individual categories. But again, that's more of a high level thing that you can just understand in terms of what does how this function actually do, right? You don't need to know the implementation details. And so in scikit-learn, you have a one encoder class, and basically what this class does is it basically goes through our a data frame object that simply has one column in this case, which is housing underscore cat has only one column. And what it does from that point is it converts each of the values into ones and zeros, each of the values here that you can see right over here. Let's go ahead and print out, first of all, the housing underscore cat dot head. And let's go ahead and see what that outputs. So you see here that this, remember, it outputs each of the individual rows, particularly the ocean proximity in this particular case. Now with this one, what it does is it creates a new one-hot encoder instance here for the object, and then it calls the fit transform function on this object, against this object. Okay, so from there, what it's able to do is we pass in the housing underscore cat, and it goes through each of these values, fit underscore transform. And remember, fit underscore transform in the original encoder class, what it does is it learned each of the categories in the housing underscore cat as well, and it replaced it with the number. And so in this case, it's learning each of the categories and it's replacing it with a number. In this case, it's going to be a number either 1 or 0. When we print out the output, let's go ahead and print this out. So let's go ahead and print that out. And let's go ahead and comment that out. What we get here is we get here a sparse matrix. This is a sparse matrix. What a sparse matrix does is it basically gives you a coordinate along with a value. So you see here that you have a coordinate 0, 1. 0, 1 refers to where this value would have been had it been an array, had it been a NumPy array. Now you're noticing that all the values are 1, and you might say it should be zeros as well, right? Well, the reason for that is because the sparse matrix actually only records the 1 values. It doesn't record the 0 values because 1s are obviously unique. All the other values and hence um, would be 0. So in this case, we have, you notice here, these are arranged going through each of the individual rows, as you can see here. So in this case, you have 0, 1, and 1, 4 correspond to 1. So that means in row 0, if I had to ask you, what are the 0 values, which data values or positions or coordinates, I guess you could say, in row 0 had a value of 0, you would say, okay, 0, 1 doesn't, 0, 2 must then, 0, 3 must, 0, 4 must. And then we stop. And also 0, 0 also must have a position of a value of 0. And then 1, 0, 1, 1, 1, 1, 2, 1, 3, and then 1, 4, we stop there. We go to 2, 0, and then 2, 2, 2, 3, right? And so on and so forth. Because all the other values that are missing correspond to 0. And how do we know that we stop at 4? Well, the reason for that is because, again, we only have 4 values, unique values in this case. We have 5, but again, this is indexing, so it's only 4. Okay, so 0 is the starting position. And also, you could probably write some code to find the max value as far as your y value is concerned in this case. But that's how it's like. This is what a sparse matrix is. It's corresponding, again, to an array. Let's go ahead. I want to show you the array just that way you can see it. So if you call the the toArray function against this sparse matrix, what it'll do is it'll print the array format of this. Now we don't store it in an array just because storing ones and zeros in an array is not very helpful. Okay, let's go ahead and first of all limit this down a little bit. Okay, so we have that here. We see here, this is what the sparse matrix would look like. Now again, it's dot dot because we don't want to print out everything. But you're seeing here how this works. So you have 0, 1, 0, 0, 0, and then 0, 0, 0, 0, 1. Now if you look at the coordinates and looking at the values, you're noticing how these are corresponding. So at, not an x value really, I shouldn't have said x value, but at the 0th position from the outer array, right? At the 0th position, corresponding to the first index position inside of the inner list, it's corresponding to a value of 1. And then in the first row, in this case would be this row, corresponding to a position of 4, or yeah, 4 would be right over here. 4, it's corresponding to 1. And so we're able to get a coordinate to value type of relationship for each of them. And that's very useful. And also this preserves memory because we're only recording the ones instead of using a NumPy array output instead. Okay, so that's interesting. You learned about how the sparse matrix worked there. Now, from there, now that we're able to get this housing cat underscore one hot, or one hot encoding in this case, we can also get the categories. So it does store the fit transform function in the OneHotEncoder class, does store the categories similar to the OriginalEncoder when you call the fit transform function. And so let's go ahead and print that out there, just that way you can see that. And you see it's a very similar thing there. It stores the unique categories. Now you might say, okay, shouldn't the unique categories be zeros and ones? Well, no, of course not, because that's the purpose of the OneHotEncoder. That's the first thing. And the second thing is, even in our previous example, we saw that it only displayed the where is that? Oh, here, right over here. It only displayed the original values in the housing tab. Okay, so only the original values. Okay, so that's the output there, and we're able to get that in an array format or in the other format. We'll talk about how we can insert that back into the pandas data frame in the next lesson, though. Although this lesson has been long enough, I think it's been roughly around 30 minutes, past 30 minutes or so. But what are we covering today? We covered how we can convert text and categorical attributes into numerical attributes using the OriginalEncoder class in the scikit-learn library, the fit underscore transform function, updating the categories, NumPy array in that case, and filling it up with unique values. we discussed how we could do that and convert it into numerical output based on those unique values in our column, the ocean proximity column, which is a categorical attribute that we sent in as a pandas data frame. But then we decided that that wasn't very sufficient because the machine learning model would be able to learn information about that data that didn't really exist. It would be able to learn correlations that simply did not exist. And so then from that point, we used the OneHotEncoder, not the OneHotEncoder, what was it again? Yeah, the OneHotEncoder object. We used that class in order to assign zeros and ones, assigning a 1 to the hot value, which is the most unique value, and a 0 for all the other values. In that case, we chose inland as being our most unique value there, and we were able to set zeros and ones. We learned what a sparse matrix was. We learned how we could convert a sparse matrix to an array, how to use the categories underscore property in the original encoder as well as the OneHotEncoder class when we declare it as an object created at runtime. All right, so that's what we covered in today's lesson. In the next lesson, we're going to move forward